Okay. So I think that last time we arrived at describing the chemical equilibrium. Well, in particular, we have written the chemical equilibrium in terms of a law, this is called the law of mass action, that basically says that the product of the concentrations to the power of the stoichiometric coefficients is a quantity that depends at equilibrium only on the temperature and the pressure. So if I have a certain initial concentration of different particles, different molecules, I can compute this quantity, and depending on so from a comparison with the reaction constant, I can immediately say in which direction the reaction will go. So this is a very useful tool in the sense that it allows me to compute in which direction the chemical equilibrium is reached, and also it will allow, at least we will just explore one example, but the formalism is general, which is the thermal ionization of atoms, which is a problem that, if you want, is very common when you have to deal with plasma. In which you have a certain a gas at a certain temperature, and a certain numbers of electrons drip out of the atoms, and then you form a plasma of ions, electrons, and of course also neutral atoms. Okay, so it's a very general problem, and it's mostly useful when you deal with plasma physics or physics of, for instance, of the matter of stars, or well, any environment in which such a situation can occur. So before going on with that, I want just to make some short a short note about the chemical potential that we derived last time. And in particular, we saw that, let me see, where do we are? Yeah, okay, so this was the chemical potential for ideal gas. So mu is equal to kdT. Then there is the logarithm of a ratio between particle density and the product, if you want, of the particle density times the thermal wavelength cubed. Well, we basically have this, right? So it's n divided by b lambda cubed, which is equal to kBT log of n lambda cubed, where n is the density. And now this equation is valid for ideal gas, first of all, and this gas must be of classical particles. Because this was derived in the context of classical mechanics and within the microcanonical ensemble in particular. And we already said that, but this we will see better when we introduce quantum statistics, that if you want to use a classical description of your system, you have to be sure that the product of n times the wavelength cubed is much smaller than 1, which means that the density is very small and or the temperature is very large. Okay, so these are the conditions. This is the condition for which a classical description is correct. And of course, when n lambda cubed is equal to 1, or is close to 1, we are in the realm of quantum mechanics. So we cannot use this formula anymore. Okay, so here we will have quantum correction. So, since we have to use this formula in the regime in which this n lambda cubed is less than 1 or much less than 1, that means also that mu is negative.
Prof, scusi,
Sì?
potrebbe abbassare la videocamera perché sta riprendendo una grande fetta sopra la lavagna.
Ok, dimmi tu quando, fino a qua?
No, ancora un pochino. Oh, basta.
Così?
Per me sì, non so
Ah,
gli
ok.
altri.
Ok,
Però sembra
ok. Allora abbasso pure la linea, il bordo inferiore, perché effettivamente avevo dei problemi a visualizzarla un po' oggi, questa cosa. Mazza, questo è sporco più. Ce ne sono altri. Vabbè. Quindi scordate che ridisegno il confine, quindi
sì,
stiamo
va bene.
più o meno. No, più o meno va, ok. Okay. So then I was saying that mu is negative for classical and ideal gas because of this condition. Okay. Also remember that. Let me. Oh, man, poi si vedrà a causa della nebbia. Che stavo dicendo? Ah, sì. So when you work at fixed pressure and temperature, the second principle of thermodynamics tells you that basically what you minimize is the Gibbs free energy, and the variation of the Gibbs free energy at that condition is mu dn. Okay. So then, what does it mean? That if mu is larger, well, if mu is negative, when you add particles, that minimize, well, that lower the Gibbs free energy. Okay, so that is good. Okay, so basically, in such a system, if you have well, this is the first thing I want to say. The second one is that if n is very small, then mu is negative and it is very large, not because of this logarithmic divergence. So that means that if you have a very small density gas, and you try to, let's say, put some new particles inside that, then it's very convenient, not because mu is very large and is negative. And at the end, this is also, let's say, in agreement with the fact that we know that when you have this usual box with two partitions, and one in which the density is large and the other one in which the density is small, then of course we know that the gas, the particles will try to follow, to flow and towards the region with the smaller density, which means a larger, well, a more negative chemical potential. Okay. So yeah, so this is the first thing I want to remark. And remember this, that now this is negative for classical and particles and ideal gas. And actually, when we will introduce the correction from quantum mechanics, we will see that for fermions, this chemical potential can be positive at very low temperature. And for bosons, there's something else that is going to happen, which is the Bose-Einstein condensation, for which at some point mu becomes, well, from negative becomes almost equal to 0 within the Bose-Einstein condensate. Okay, so we will see this in a few weeks. Okay, so this was the first comment that I need to do. So there is another one that, so at some point we decided, following, I think, a tradition from chemistry, to divide the chemical potential in two terms. One which contains just the pressure dependence, so the total pressure, if you want, and the other one which contains well, this chemical constant, which basically contains some information on the specific gas you're dealing with. So in particular, in this formula for this chi of T, which was this kBT log of lambda cube, and then there is a kBT in the denominator. And the lambda, remember that lambda is a h divided by 2 mi kBT. So you see that, well, one specific feature or property of my particles is the mass. And of course, if the mass is different at fixed temperature, the lambda will be different, and therefore this will characterize this function key, which depends on the specific particles we are dealing with. So the first thing is the mass, of course. Now there is another thing, which is the possible degeneracy, that I would like to introduce at this level, degeneracy, just providing you let's say a sort of argument. We will see in a better way in the future how this degeneracy factor can appear in the formula of chemical potential of key. But the degeneracy could be, for instance, due to the fact that particles have a spin, typically. Okay? Spin degeneracy. And how do I modify this function when I have a certain degree of degeneracy? We can do the calculation in the future when dealing with, well, when we'll study the canonical ensemble and the grand canonical ensemble in a better way, in an easier way. But the argument maybe can be also explained in the following way. So, just a short reminder. When we have calculated the entropy from the microcanonical ensemble, well, at some point we have to do this integral over dp and dq, which are the well, the usual canonical variables, and in particular, for what concerns the integral over the coordinates, we have a contribution to the entropy, which was proportional to kb log of b to the power of n, plus other stuff. Okay, and this b to the power of n comes from this multiple integral over space of the coordinates. Okay. Now, if there is degeneracy, well, these integrals basically get a factor of g. So basically, I have the integral over the coordinates, and just need to add a factor g, which takes into account the degeneracy, which could be the spin, for instance, and therefore I will have, if you want, an additional contribution to the entropy, which is related to the degeneracy, which will be something like kb log of g to the power of n, where g is the degeneracy, and which is of course equal to nkb log of g. And now you see that since the chemical potential is minus T times the derivative of entropy with respect to density, I will have an additional contribution to the chemical potential which will be something like minus kBT log of G. Okay? So then when I put everything together, at the end I have a G at the denominator of the chemical potential that I was writing, that I wrote before, and therefore in this chemical constant I will have a degeneracy factor which appears here in the denominator. Okay? So this is well, a motivation for that. One has to modify the integral over the space variables in presence of degeneracy, and we'll have an additional factor of degeneracy, which appears here. So then we see that in this function here now, apart from the temperature, we have the mass of the particle, which is hidden here in the lambda, and the degeneracy. Okay? So which are two things that characterize indeed the type of particle scientifically. And okay, this is a possible way to justify the degeneracy factor, but we will see that there is a simple way once we introduce the canonical ensemble. Okay, but just for the canonical, for the moment, just remember that we have an additional factor of G, which could be important. Okay, so this is the two things I need to specify. And yeah, so now we can go on. Actually, there is another quantity that I need to add to this chemical constant that I will explain in a moment. But before going to that, let me just remind you which was the point of last time, thermal ionization of atoms. So I think we derived we wrote the mass action law in the following way: C plus C minus divided by C0, where this is the concentration of positive ions, this is the concentration of electrons, and this is the concentration of neutral atoms. This is equal to 1 over P, total pressure, times this function A of T, which is a complicated function, which was the exponential of the sum of minus stoichiometric coefficient times chi. Okay, we will see in a moment. Okay. Well, actually, let me write it down immediately. So A of T was defined as the exponential of minus 1 kBT, and I have the sum over J of the stoichiometric coefficients times the chemical constant. Okay. Where the stoichiometric coefficients, if we call this particle 1, well, if you write the reaction in terms of A plus electrons equal to 0, this gets a factor 1 as a stoichiometric coefficient, is 1 and is minus 1. Of course, I can write also the opposite, it will not change anything. Okay? Just arbitrary. The sign of the stoichiometric coefficient is just arbitrary in this respect. Okay, so now I have to compute basically this quantity. Well, the three chemical constants for the three components of the gas. Then I have to do the exponential, and then I will have my mass action law. Okay. So let's try now to compute these three chemical constants. So the general formula is the following: is a kBT log of, here I have lambda cubed, which is h cubed divided by 2m pi to the power of 3/2, 2m pi to the power of 3/2. Then I have a kBT at the denominator, which multiplies a kBT to the power of 3/2. Therefore, I have a kBT to the power of 5 divided by 2. kBT 5 divided by 2. And now, okay, we know also that there is a degeneracy, G. Okay. So now this is the general formula in which I have, I can explicitly see which are the two constants in this case that characterize my particle, my gas, degeneracy and mass. Okay. So the formula for the electrons of this chemical constant will be the following. Let me see, yeah, it's convenient to write this in the following way. So it's minus 5 divided by 2 kBT log of kBT, where I'm splitting this part containing the temperature. Then I have plus kBT log of h cubed 2m pi 3/2. And I have the degeneracy of electrons, let me call it G minus, where G minus will be equal to, for electrons, it's a spin degeneracy. Okay, it's two states corresponding to the spin of the electrons. Allora, io devo cancellare perché sennò non si vede, quindi, so I write now the same formula for the two components of atoms. So I will have a similar quantity now, which is K plus with the same term. The first term is the same, is the log of kBT, and then the second term contains now kBT log of h cubed. Here I have a 2m pi. And now this m is different from the m that I had before. Let me call it m plus, where m plus is the mass of the ions. Questo è elevato alla 3 mezzi, so così to the power of 3/2. And then I have the degeneracy again, which is G plus, which will be the degeneracy of this ionized atom that I will not specify. I will take as a parameter that I can change. And vediamo se c'ho tutto. Now here you have to add another quantity that again I will justify in the following way. Let me call it epsilon 0 plus which correspond as an additional contribution to the chemical constant, which corresponds to the energy of the ground state of the ion. Well, actually, what is important, it is always this, the argument is always the same when dealing with chemical potential. What is very important is the difference actually in chemical potential. So now what I have to consider is the fact that the energy, if you want the binding energy, well, the ground state energy, better to say, of an ionized atom and of a neutral atom, they are different because in one case, well, in one case there is an electron missing, and in the other case there is an electron with a binding energy, but in any case there is an electron. So there will be a difference which is characterized by a constant actually, that somehow is telling me the information about the fact that in one case I have a bound electron, whereas in the other case I do not have these electrons, that the gas has been ionized. Okay? So actually what is important now is the difference between this constant here and the other constant that will appear in the same formula for the neutral atom. And this will be interpreted as the ionization energy. So let me write down the same formula for the neutral atom, which is chi0. Okay, the first term is always the same, kBT log of kBT plus kBT log of h cubed. Here I have a G0, the degeneracy now of the neutral atom. Then I have a 2m5 to the power of 3/2. And here let me put m plus. So when I'm saying that the mass of neutral atom is almost equal to the mass of the ion, which at the end of the day is not a bad solution in the sense that the difference in electron, which has a small mass with respect to the atom, and the binding energy. So, I mean, they are basically the same, ok? Quindi ho questi termini qua, and then as here I have a constant that I call epsilon 0 plus, and here let me have the constant which is epsilon 0, 0, which again has the interpretation of, if you want, of the ground state of the neutral atom. Now, what you will see in a moment is that actually what is important is the difference between this and this basically the ionization energy. So the energy that I have to provide to my neutral atom in order to unbind the electron. Okay? So indeed, let me now compute this sum that appears in the exponential. So you have to compute the sum over j of mu j times this key j, where these mu j are 1, 1, and minus 1. So therefore, the terms that contains just the temperature, two of them they cancel, whereas the other one provides a contribution which is 5 divided by 2 kBT log of kBT. Then I have plus E0 plus minus E0, 0, which I will call I, and this is indeed the ionization energy. Okay, then I have plus, well, the logarithm, the KBT logarithm. Well, here I have all the three contributions inside. So one is h cubed. Then I have the degeneracy of the electrons, which is 2, and I fix it to 2. Then I have 2m pi to the power of 3/2. And similarly, I have the same coefficients for the two other components. So there will be a g plus and 2m plus pi to the power of 3/2. This is for the ion. Whereas for the neutral atom, I will have a G0, diciamo così. Okay, let me move a little bit this ionization energy. Here, I. Then I have, so I have G0, 2m pi and plus pi to the power of 3/2 divided by h cubed. And I can close this. So now you see that there are some cancellation, of course, of this one and this one, this one and this one. And then I'm left with h bar divided by 2, g plus g0, and then there's this additional factor, which contains the mass of the electron. Okay, so then at the end, the sum over j of mu j, Ej, is equal to minus 5 divided by 2 kBt log of kBt. And then I have plus the ionization energy, I. And then I have this additional factor, plus kBt log of, so h cubed, and there is a 2m pi 3/2, questo, and then the ratio between the degeneracy G0 and G plus. And I think I have everything there. Okay, so now I can compute these, questo è il cancellino, eccolo qua. So now, well, I can compute this A of t, because A of t is the exponential of 1 minus kBt, and then there was the sum over j of mu j pi j. And so here I just need to now to introduce the terms that I have computed before. So basically, we'll have three factors. One of them is, so here I had 5 divided by 2 kBt. kBt comes the log of kBt. So then I will have a kBt to the power of 5 divided by 2. So the first term will be kBt 5 to the power of 5 divided by 2. Then I have e to the minus I divided by kBt, which is indeed the term, let's say the suppression that one would have guessed, well, intuitively, in the sense that to ionize a gas, somehow I have to compare the ionization energy with the thermal energy. Okay, so there must appear a suppression, an exponential suppression, which is provided by this formula. Okay, this was expected from the beginning. Well, the difference now is that there is an additional prefactor which has this power of temperature that, of course, will change the property of the ionization, okay, as we will see in a moment. Okay, then there is, well, 2m pi, where m is the mass of the electron, then I have h squared to the power of 3/2, then 2g plus divided by g0. Then I can conclude, if I write again my mass action law, that the ratio of the initial concentration, well, the concentration of ions and electrons divided by the concentration of neutral atoms. Now this is 1 over the pressure, and then there is A of t, okay, which is this formula here. A of t. Now I can write P as, let me see, as kBT divided by volume times n, where n represents the total number of particles. Okay, so this n is the sum of electrons plus ions plus neutral atoms. Okay, so if you want, this is the total pressure, which is the sum of the partial pressure, which are proportional to the particle densities for the different particles. Okay. Yeah, so when I introduce this, the pressure in terms of kBTm divided by V, then my mass action law has this formula, has this form, 2g plus divided by g0, I put in front of my formula. Then I have V divided by N, which comes from the pressure, the inverse of the pressure. And then I have a 2m pi divided by h squared to the power of 3/2. Okay, where this m is the mass of the electron. Okay. Then I have a kBT, here was to the power of 5 divided by 2, but then I have this correction, then I will have a kBT to the power of 3/2. And finally, I have my exponential suppression. Okay, so this is the mass action law for the process of ionization, which is written, as you see, in terms of temperature. Of course, the temperature will play a major role. And also you have some other features or properties of my gas, the mass of the electrons, the degeneracy, volume, and the total density of the gas. Okay, so now what I want to do is to study the degree of ionization as a function of the temperature. So let me introduce now, forse cancello sopra e lascio questa per un momento. So let me introduce some notation. So let me call n plus equal to n minus, which is the number of ions, which is also equal to the number of electrons. And it must be, of course, they must be equal by charge concentration. No? So m is the total number of particles, as we said before, total number of particles. So it is the sum of electrons plus neutral and ionized atoms. And let me also introduce Na, which is the sum of neutral atoms plus ionized atoms. Okay? So once I introduce this notation, so let me remove this formula now. I can write now in a different way the concentration. So in particular, C plus, which is the concentration of ions, is N plus divided by N, which is equal to N plus divided by Na plus N plus, where Na contains the atoms and N plus contains the electrons or the ions, and is also equal to C minus. And let me see come che l'ho scritto questo. Just a moment. Okay, I will need to check this. Okay, C0 is the concentration of neutral atoms, which is equal to the total number of atoms minus the total number of ions divided by Na plus N plus, Na plus N plus, sorry. And yeah, so then let me introduce alpha, which is the ratio between N plus divided by Na, and this is the degree of ionization. So which is the ratio between ions and total number of ions, total number of atoms, sorry. Okay. Now I can compute C plus C minus divided by C0 by introducing these quantities. And okay, so this is the square of this quantity, so which is N plus squared divided by Na plus N plus squared, which is this guy here. Then I have to divide by C0, and C0 is N Na plus N plus divided by Na minus N plus. Quindi cosa che succede? Che si cancella qualcosina. So this is a remove. Ok, scriviamo qua. So let me see. Here you have N plus squared, so C plus C minus C0 is N plus squared divided by Na squared minus N plus squared. So now let me divide by, let me see, com'è che mi conviene fare? I divide by Na squared, denominator, numerator and denominator. Therefore, I will have alpha squared here, 1 minus alpha squared, where alpha is the degree of ionization, which is the quantity we are interested in. And because of the mass action law, this alpha squared divided by 1 minus alpha squared is V n 2g plus divided by g0. Well, and then I have the usual factor. So 2n pi k dt h squared to the power of 3 alpha, and then I have the exponential k dt pi. Okay. Okay, so this can be rewritten in a a slightly different way. Let me see. So I have alpha squared divided by minus 1 minus alpha squared. Then I have V. Now n is the sum of NA plus and plus. Okay, then the rest is the same. Sì, il resto è uguale. So 2G plus G0 2m pi kdt divided by h squared to the power of 3 half exponential of minus I kdt. Now let me multiply here and divide by NA. Yeah, so let me divide by NA and multiply by NA. So I will have my N, yeah, so NA at the denominator. Sì. And then I have NA here and NA here. Okay, that is fine. Then this is V divided by 1 plus this alpha again, this NA. Okay, then okay, the rest is the same, 2G plus G0, 2m pi kdt h squared 3 half exponential of minus I kdt. And at the end, I can, so this is alpha squared 1 minus alpha squared, I can remove a factor of 1 plus alpha, and I get the final equation, which is the following. So is alpha squared 1 minus alpha is equal to, let me put this factor of 2, which is the electron degeneracy, times a function phi, which is a function of volume and temperature, Vt, where I have defined V phi of Vt as this quantity here that contains, well, is all these factors. So it's a V divided by Na, V divided by Na, I have a G plus G0, 2 pi n kdt divided by h squared power of 3 half. And then I have a e to the minus I kdt. Okay. Vediamo se è giusto, B n0 G più 2m fatti. Okay. Now this equation here is called Zaha. I don't know how to pronounce it. I think it's Zaha equation. And as you see, that provides the degree of ionization as a function of, well, this quantity here that contains well, volume, which is usually fixed, to the number of atoms, which is also say a fixed quantity, in the sense I will start with a fixed quantity, fixed number of atoms. And well, and then there are these constants that characterize the degeneracy. Here I have the mass of the electrons, and here I have the ionization energy. Okay, so now you see that here I have a temperature to the power of 3 half. So with a little bit of fantasy, I can write this function, well, this function here in the following way. As T divided by T0 to the power of 3/2 exponential of minus I divided by kBt, where I have introduced a temperature which will be a characteristic temperature that, of course, contains some physics, and we will actually try to compute these, because this quantity is I-dimensional, no? Because it must be, let me see, it must be, yeah, is a alpha which is no dimension. So also phi must be a dimensional, and then since I have here a t to the power of 3/2, this must be divided by a t0 to the power of 3/2, where I have defined t0 in the following way. T0, by definition, is, well, I have to put everything which is in this formula but for t. So then T0 will be, let me write it down, V divided by NA, G plus G0, 2 M pi KB divided by H squared to the power of 3/2. No? So everything which is there, so questo è questo, G più G0, 2 pi KB, H squared, then of course I have also, yeah, that's it. Of course it must be to the power of minus 2/3, right? Questo volevi dire?
Sì, esatto.
Sì. Minus 2/3, okay? So this quantity here must have, if I have done the calculation correctly, must have the dimension of a temperature, and we will try to estimate in a moment which is this temperature, which of course, as you see, depends only on the, well, some macroscopic quantities which I fix in my experiments, and then some microscopic quantities which are basically just the ratio of degeneracy in the mass of the electron. Okay. Okay, so we will use this formula now in a moment just to make some numerical estimate on this value of T0. Okay? Che faccio? Faccio da qua. Questa è la Zaha. Now I can also solve this equation because actually I have alpha squared, which is equal to 2 phi minus 2 alpha phi, and the solution is that alpha of T and V, which is the degree of ionization, will be minus phi, this function here, plus T squared plus 2 phi. Okay, so this is the solution of the Zaha equation that provides me the degree of ionization as a function of temperature and volume, which is hidden in this function phi. Now, of course, here there are two solutions, but I have taken just the one with the plus in order to be sure that this is a positive quantity. Okay, the other one will be unphysical. Now, what happens that, okay, so phi has a scaling for what concerns the temperature of this type. So phi scales as t to the power of 3/2, and then I have an exponential of the ratio between ionization energy and kBt. So you see that when allora, vediamo che succede. When the temperature is very small and phi will go to 0, so for t going to 0, also phi will go to 0, and I can also infer what is the scaling of the degree of ionization, and alpha will scale as the square root of 2 phi. Okay, So when the temperature goes to 0, the degree of ionization, well, is 0. Well, it goes to 0 as I would expect, and the scaling is a square root of 2 phi, that in principle is a useful scaling if I have to compute these ratios. And whereas what happens when in the other limit, so this is the low temperature limit. Let's see what happens when I have the high temperature limit. In the high temperature limit, of course, this function phi goes to diverges as 3 to the power of 3/2. And let's see what does the degree of ionization. This was minus phi plus, and then I have a phi squared plus 2 phi. Era questa, vero? La formulina, sì. Okay, so here I can do, if you want, a Taylor expansion, in the sense that I can do the following trick. So this is 1 plus the square root of 1 plus 2 divided by phi. Vediamo se è corretto. Yeah, so this is a minus, of course. And then it's 1 plus 2 divided by phi. Okay? Giusto, sì. Okay, now I can do a Taylor expansion if you want. Taylor expansion in powers of 1 divided by phi, which is an infinitesimal quantity. And I need to go to the second order. Okay, I don't need to do these calculations, but basically what you get if you Taylor expand this quantity is a scaling, which is 1 minus 1 divided by 2 phi. Okay, if you Taylor expand this quantity. Up to the second order in 1 divided by phi squared. Okay, so you see that when phi goes to infinity, the degree of ionization goes to 1, so I have a full ionization as I would expect, and I also can, well, I have also a useful scaling, which is this 1 divided by phi. Okay. Now to make some, so this formula, of course, can be used in several problems. I don't know if you ever met this Zaha equation. Have you ever met this formula in your...
Un'altra forma in cosmologia.
Ah, infatti, vedi. Yeah, in cosmology, in che contesto? Raccontami. Nella parte di nucleosintesi?
Credo di sì.
Okay. Yeah, so indeed, as I told you before, it's a formalism that can be useful in several situations. Indeed, also in cosmology. I didn't think about that before. And so now, apart from this formula that you can use in a situation in which you need it, in principle, let me just put some numbers in order that we have the feeling of what's going on. So in particular, you see that in the problem, there's a function of phi, which is a function of v and t. This is t divided by t0 to the power of 3/2, and then there is e, so to the power of ionization energy divided by kT. So there are, well, two scales which are basically characterizing my system. One is the ionization energy, which of course is something that from the beginning I would have expected to play an important role. But there I have another scale, okay, which is this T0. This is a prefactor which is important. And well, unfortunately, in statistical mechanics, many times the role of the prefactor is very important, and one has to do the calculation for doing that. So in the sense that although like a simple argument like this one is of course correct, in some cases the corrections due to the prefactor can be important, and for computing these prefactors one has to unfortunately do the full calculations. Because you see here that a new scale appear, which is T0, and let's try to estimate this T0. So now T0 was defined as, okay, this to the power of minus 2/3. Now let me write in this way, is NA divided by volume to the power of 2/3 this time. Then I have G0, G plus to the power of 2/3. Then I have H squared, poi che c'ho 2n pi kb, 2n pi kb, which was to the power of minus 2/3 and to the 3/2, and therefore I have this h squared divided by 2 pi n kb. Okay, so this should be the right formula for T0. Let me check if I have everything there. Sì, direi che c'ho tutto. Okay, so let's try to estimate this number. So let me take NA equal to, let's take a density of, well, a number typical of a macroscopic system, which would be something like 10 to the 23, no, as a scale of Avogadro number. Let me take the volume as 1 meter cubed. So let's say it's 10 to the power of 15 Fermi squared, cubed, sorry, cubed. Let me consider G0 equal to G plus equal to 1, just for an order of magnitude estimate. This, of course, will depend on the arguments that you have. And yeah, so let's work in natural units, because I'm mostly used to work in natural units. So let me see, natural units, KB is, so the Boltzmann constant is 1. Of course, also H is 1. And M, which is the mass of the electron, is 0.5 MeV. So then you see that here you have a quantity that contains, let me see, a Fermi squared, the denominator here, because I have this volume is Fermi cubed, so then I have a Fermi squared, and then I have a MeV, the denominator, and the rest is adimensional. So in order to get the proper number, well, in natural units, well, let me write first of all natural units this quantity. So this is NA divided by V and 2/3. Okay, this is 1, so I will not put this 1. So now you have 1 divided by 2 m pi. So KB is 1, H by H is 1. Well, actually, to be fully consistent, and I think I haven't done this, unfortunately. Okay, it's a small correction, it's a correction. Ma non no, no, l'ho inclusa. No, sono stato bravo. Okay, so let me multiply this by 4 pi squared. And if I do this, this is h bar. Okay? Ho fatto questa cosa. So I have an additional 4 pi squared here. And now you see that the dimensions are 1 over MeV and 1 over Fermi squared. So then to get the proper dimension for a temperature, which in natural units has the dimension of an energy, I have to multiply by 200 MeV Fermi squared. Okay? Which is of course is h bar c, and this way I get the proper dimension, not because MEV here, then I have MEV squared, so I have MEV, and Fermi squared cancels with this Fermi squared. Okay, so now if you do the calculation, you get the T0 as a scale in terms of energy of the order of 10 to the minus 9 MeV. Okay, and a useful conversion factor that is that sometimes is useful to remember is that a temperature of 10 to 10 Kelvin is almost equal to 1 MeV in natural units. So therefore, so this is a, if you want, a conversion factor. Okay. So then, if you want, this T0 in Kelvin is a few Kelvin, is a few degree of Kelvin. Okay, so this is few degrees in Kelvin, because it will be of the order of 10 Kelvin or something like that. Okay, a few degrees. So you see that this T0 as an energy scale, or if you want, as a temperature scale, is very small. And actually, this well, if you want this scale, this energy scale, or this temperature scale, which is much smaller than the typical scale of the ionization energy. Because for the ionization energy, we can imagine a typical order of magnitude could be of the order of electron volt. Okay, for instance, if you take hydrogen, ground state is 13 electron volt. Let's say is of the order of the electron volt, which is in terms of temperature is of the order of 10 to 4 Kelvin, roughly, perché devo dividere per 6 questo. So then you see that you have a ionization temperature, which is 10 to 4, and a scale T0 in the prefactor, which is of the order of a few Kelvin. Okay? So this difference in these two scales actually is responsible for a, let's say, significant ionization, even if we are not sitting exactly at the ionization energy. Okay, so we can have a good degree of ionization, even if the temperature is not has not the scale of the ionization energy. So to do this, we can try to estimate in the following way, which is the degree of ionization and which is the suppression factor. So, okay, so so these are two different and two very different energy scales. Now, if you want to estimate, just to give some more intuitive feeling of what's going on, suppose that we fix phi of the order of 1, which in the formula of before as a solution of the Sacra equation means that alpha is of the order of 0.7. So it's a 70%, if you want, of ionization, which is a good degree of ionization. Okay. Now, phi is equal to 1, and phi in turn was equal to a temperature divided by T0 to the power of 3 half, and then this minus ionization divided by kd T. So now let me put here C, just to indicate Tc, if you want, as a, let's call it critical temperature. Is not really a critical temperature in terms of phase transition, but let's call it critical temperature, just to make a difference between T and Tc. Tc is the value of the temperature for which phi is equal to 1. Now, from this I can get that the exponential of I divided by kb Tc is equal to Tc divided by T0 to the power of 3/2. Then I can make a log of this. So I divided by kb Tc is the log, well, is 3/2 the log of Tc divided by T0. Okay? Vediamo cosa ho combinato qua. Tc divided by Tc divided by T0, and let me introduce, aspettate che se no faccio confusione con i simboli. Allora, questo era Tc diviso T0. Okay, let me write it in a better way, otherwise we can get confused. Is ionization energy divided by T0. So I multiply and divide by the ionization energy. Okay? So then this is equal to 3/2 the log of ionization energy divided by T0 minus minus 3/2 the log of, again, ionization energy divided by Tc. Ionization energy divided by Tc. Let me see why I'm doing that. Yeah, okay. So I divided by T0 minus 3/2 log of Tc. Okay. Now, well, let's say that Tc will be not far away, not very far away from the ionization energy, because it will be anyway a large temperature, because I'm trying to see what happens when I have a 0.7 degree of ionization, whereas I divided by T0 is large. So this is large in comparison with I divided by Tc, because here I have a factor of 10 to the 4 Kelvin divided by phi Kelvin, whereas here I have 10 to 4 divided by a temperature which will be, say, closer. Of course, Tc must be larger than T0. So this is just to make basically a simple approximation and say that this is 3/2 log of I divided by T0, and this allows me to find Tc as in this approximation as a function of I and T0. No? because at the end I can conclude. So this was I divided by K T C, and so at the end I can compute from here TC, and TC is equal to I divided by KB, and then I have a 3/2 the logarithm of ionization energy divided by T0. Okay. So from which you can have somehow a feeling on how small, let's say small is or how suppressed is Tc with respect to the ionization energy. Okay. So this will allow to make a comparison between I and Tc. Okay, so then you see that to get a degree of ionization of 0.7, which is of course just, well, let's say quite important high degree of ionization, which is this Tc. Well, actually, I need to reach a temperature which is a factor of 3/2 log of this quantity less than I. Okay, so now if this is I divided by T0, it was 10 to 4 divided by few Kelvin. So let's say that this is of the order factor of 3 or 4 in front of the logarithm. So this could be easily be of the order of few tenths as a suppression factor. Okay, so I don't need to go to the ionization energy to have an important degree of ionization. Just need to go to, let's say, a factor of 10 less of energy. Okay. Okay, so this long calculation was just to show that when you do statistical mechanics and you ask yourself questions about, for instance, chemical equilibrium, you can get also some interesting information on the kinetic. Well, not really the kinetic, but the direction in which a reaction will try to go in order to fulfill the second principle of thermodynamics, and also in this context to compute in a plasma, in a mixture of ionized atoms and neutral atoms and electrons, which is the degree of ionization, which is of course an important quantity if you need to do some calculation, as your colleague was saying I guess in Big Bang nucleosynthesis, maybe. Era quello il contesto?
Sì.
Okay. Good. So ionization is also a process interesting from the point of view, if you want, of phase transition, in the sense that you can interpret it as a sort of very, very smooth phase transition. So actually, the ionization as would be like similar to what is called crossover, in the sense that thermodynamical quantities are basically there's no ionized phase which is separated with respect to a not ionized phase. It's a gradual process, okay? But it's a sort of, if you want, a phase transition from a gas which is neutral, so there's no charge flowing around, to a plasma, which is considered to be, let's say, a possible phase for matter. So in this transition, if you want, for a neutral gas to a plasma, is the ionization process. And you can interpret it as a sort of phase transition and do a very smooth one. Okay. Okay, so now let's conclude this part of the microcanonical ensemble, and we move to the canonical ensemble, which is actually the most interesting from the point of view of the applications. Canonical ensemble. Okay, so the idea is to basically remove the constraints on the that we need to fulfill in the microcanonical ensemble. So just to remind you, the microcanonical ensemble we had V, N, and E fixed. So we are dealing with a system which is completely isolated from the environment. So the volume is constant, the total number of particles is constant, and the energy is constant. There is no exchange of energy between our system and the rest of the world. Okay? And within this, let's say, constraint, we let's say how to say. The microcanonical ensemble, the challenge is to compute, if you want, the number of microscopic states which are comparable with those constraints. So in the case of ideal gas, which is a case in which there is no interaction between particles, the form, the geometrical form, if you want, of the volume of the phase space occupied by the microcanonical ensemble is rather simple because it's basically a shell, or it's a sort of spherical shell, and it's a spherical shell by considering the fact that the energy is determined up to an error delta, we said last time. And actually, the calculation was even simpler by considering the fact that the volume of the spherical shell is almost the same as the volume of the total of the sphere. And we could compute, indeed, the volume by computing this multidimensional integral, which was somehow easy to do in the case of free particles, in the case in which there's no interaction. In that case, indeed, the constraints of energy is very simple because it's just a sphere. Now, if you can imagine how complicated is the situation when you introduce interactions among particles, first of all, which will be, of course, very, very complicated, if not impossible, in the microcanonical ensemble. And also when introducing also an external field, so something like that modifies the energy of your particles as you, for instance, the presence of an external field that could be a gravitational field, or other examples that we will see in a moment, but not today. And so if I add, if you want, interaction, and I mean interaction among particles or interaction of the particles with an external field, the geometrical shape of this volume will be, let's say, of course, much more complicated, and of course, to compute the volume will be very difficult. Okay, so the first point is this one: the microcanonical ensemble has too many constraints, so it's not very useful beyond the case of the ideal gas, because once you introduce something which is more interesting than the ideal gas, then you are in trouble. So you cannot do the calculation. It's very complicated. Okay. So this is the first thing against, if you want, the microcanonical ensemble. The second one is a more phenomenological motivation. It's due to the fact that usually, let's say experimentally, it's not very easy to fix the total energy of the system, because the system in any case will try to exchange energy with the environment. So the situation which is much more common is actually a situation in which V and N are maybe fixed. Actually, we can see in a couple of weeks that also N actually can be, the constraint on N can be removed. But typically the situation which are more useful, from the say, phenomenological point of view, are the situation in which Vn are fixed, and instead of energy is the temperature that is fixed. Okay? So the canonical ensemble will somehow allow to work, so to switch from this description of the system, which is a system which is completely isolated, to a system which is a constant volume and total number of particles, but which is at a fixed temperature, which means that in principle my system could exchange energy with a reservoir, as I will comment in a moment. So the reason for introducing the canonical ensemble is this one, if you want, which is more phenomenological, and also because, as you will see, the calculations are much easier in the sense that I have a constraint less to be fulfilled, and this will allow me to do so the calculation in a much simpler way. Actually, even more simple from the point of view of the calculations is the grand canonical ensemble, in which I also remove the constraints on the total number of particles. And actually, as we will see, when dealing with quantum gas, quantum particles, we will actually work in the grand canonical ensemble. It will be much easier than working within the canonical ensemble. But this we will see in a couple of weeks, probably. Okay, so this basically is the motivation. Now remember that when we were dealing with the microcanonical ensemble, we were computing the volume of the phase space occupied by my system, and the quantity that we directly derived was the entropy, and the connection between entropy, which is a thermodynamical variable, and the microphysics of my system is the equation of Boltzmann, no? Which relates the entropy to the volume of the phase space. Okay, so here the link between the microphysics and the macrophysics is this one, is the entropy equation of Boltzmann. Whereas we will see here that instead of using instead of using the entropy, we will actually have the Helmholtz free energy. And instead of having the volume of the phase space, we will have another quantity, which is the canonical partition function, that will allow to derive all the quantities that we need in our calculations. Okay, so let's start. So the idea, as I said before, is the following. Suppose that I have a box which is not really now the box of gas, but it's a system which is my, let's say, total system living in the microcanonical ensemble. I will explain in a moment. Okay, so suppose that this is a system which lives is a member of a microcanonical ensemble, so it has a total energy ET, total energy. Then I think I have introduced also volumes. No, I just have introduced the total energy. Okay. Well, in principle, I can also introduce the volume and the total number of particles. Okay? So total number of particles, and here is the total volume of the core. But actually, the volume here is not very important. Now, in this system, which is isolated, so the total system is isolated. And if you want, for this total system, I can write the microcanonical formalism, okay, the member of the microcanonical ensemble. But in this system, I can now define two subsystems that I call S, where S is my system I'm interested in, and the rest, let's say the complementary, if you want, of my system, chiamiamolo S piccolo per non confondere con l'entropia. Okay, so as indicated system for which I want to compute the thermodynamics, then I have another system which is R, and R stands for reservoir. Reservoir in a let's say in a meaning that you know also from general physics. So it's a system that can exchange energy with S without changing its temperature. So basically it's a system with an infinite heat capacity. Okay, so R can exchange energy with S without any change of its temperature. Okay, so if you want as an infinite heat capacity, or well, as a very large heat capacity, okay, very large heat capacity. Okay. So I have a total system which is isolated and say is a member of the microcanonical ensemble, for which I know the thermodynamics. Then I divide the total system into a small system S, which is the system I'm interested in, and a reservoir, which is a large system having a large heat capacity. The heat capacity is an extensive variable which is proportional to the number of particles. And then, well, this reservoir basically provides energy to the system S. It can release energy or it can extract energy from the source without any change of its temperature. So basically, what's going on here is that the temperature of the, if you want, instead of fixing, as I said before, the energy of the system S, I will fix the temperature, because this is in thermal contact with a reservoir, so it can exchange heat with a reservoir, and then the reservoir basically regulates the temperature of this subsystem. Okay, so for the total system, I can write the ensemble, which is the usual one for the total system. I will have in general a microcanonical distribution which is equal to a constant when the total Hamiltonian fulfills the constraints of the energy. So this is constant in the region of the phase space for which h of t, which is the total Hamiltonian, is within the error bar of the total energy. So similarly, well, actually it's the same as the description of the microcanonical ensemble that we have introduced a few hours ago. Okay, and this is 0 outside of this region. Okay, so this is the standard microcanonical distribution associated with the total system. Okay, and apart from normalization, I can, let's say, how to say, take care of the normalization at the end, okay? In any case, since there are always logarithms, or I can normalize at the end, okay? So apart from normalization, the total volume of the phase space occupied by the microcanonical ensemble, but similarly to the calculation that we have done before, is a integral in dp dq in the region for which HP has this constraint, fulfills these constraints. Okay, square and this HP minus divided by 2. Now with this symbol dp dq, I actually mean I'm not specifying the number of particles, it's useless at this point, but depending on the number of particles, depending on the dimension of my problem, of course this dp will be dp1 to dpn in one dimension, or dp1 to dp3n in 3 dimensions, and similarly for dq, okay? So I will not write now, since I'm not specifying the dimension of the system and the number of particles, let me just indicate in the following way, okay? It's just the infinitesimal phase space volume of the total system, which is actually can be factorized, if you want, in a phase space volume of the small system, okay, and the phase space volume of the reservoir system, okay. So this is associated to the reservoir, and this is associated to the system I'm interested in. Okay? Now, I can also introduce, and now this is let's say, approximation, although it's a very good approximation for a reason that we will understand in a moment. I can also introduce, in principle, a similar structure also for the reservoir, because the reservoir basically is almost coincident with the total system, because the system S is much smaller than the reservoir. If you want, the number of particles is much less. Okay, so then in principle I could introduce also sort of microcanonical ensemble also for the reservoir. There will be something like DPR, DQR, with the constraints on the Hamiltonian of the reservoir, which will be ER plus delta and ER minus delta divided by 2. Okay. Apart from normalization constant. Okay. So this will be, if you want, a microcanonical description of the system R, which is the reservoir. Now, what I will not do is to introduce a microcanonical description of the system S, because I'm not interested anymore in the microcanonical, and I will do the following thing. So remember that what is providing, so this quantity, what is providing? So remember that in general, well, when we talk about the microcanonical ensemble, we say that dV, so this is in general, is rho times dP dQ, where dP dQ is let's say infinitesimal portion of the phase space, and dV is the number of states. Okay, sì. D omega is the number of states within this volume, and rho is a probability density, no? This probability density in the case of the microcanonical ensemble was basically a constant, and this constant, of course, fulfills the constraints of having a Poisson bracket with the Hamiltonian equal to 0, and therefore this is stationary, okay? And out of this probability density, one can define all the thermodynamical variables that we saw in the case of the microcanonical. So now we can do something like this in the case of the subsystem, and I will introduce a d omega s in the following way. I will say that the number of states, or the volume, if you want, which is the same but for a normalization, occupied by the system S, let me put it this way, regardless of the state of R, and this is the crucial point, will be something like a normalization that I call A. Here I put dps, dqs, and the fact that I'm not considering the state of the reservoir means that I'm basically integrating over all the possible states of the reservoir. And so this distribution will be now something like this. And now this quantity is a rho, which actually is defining indeed the canonical ensemble associated with the system S. So what is the meaning of this? So here I have an infinitesimal volume of the phase space of the system, and if I multiply this times a probability density, I should get the total number of states of the system S, okay, which are fulfilling my constraints. Now this time, instead of introducing a constant function for the probability density, in this case not a constant, because apart from this function here, A is a normalization, basically is the total volume associated with the microcanonical description, if you want, of R. And of course, this is a function of the energy of the reservoir, and if you want, is a function of the energy of the system. Because, of course, a constraint that I have to impose is that ES plus ER is equal to E dot PT. Okay? So omega R is a function of ER, which in turn is a function, well, can be written as E total, which is a constant, once I fix my system, my total system, minus ES. Therefore, you see that this quantity here is actually a function of ES or E or ER, which is the same. Okay? So basically what I'm doing is to ask the following question. Suppose that I consider an infinitesimal volume of the phase space of the system S. Well, this will be the probability density function, and this will provide a number of states. But now I'm somehow integrating over all the possible states of the reservoir at fixed ER, or if you want, at fixed ES. Okay? So that's the difference with respect to the microcanonical ensemble. The fact that I'm tracing over the states of the reservoir. Now, once I do that, the step, the simple construction, if you want, what I'm doing there, if you wanted to put it in this way, is that if you have a DPS, DQS, DPR, and DQR, and this was a constant, and this was the d omega dot. So basically what I'm doing is to integrate over the states of the reservoir to get the probability function associated with the system. Okay? Okay, so now omega of R, now by following the Boltzmann equation, is a KB log, sorry, is the entropy. So omega R, of course, is related to the entropy of the reservoir by the Boltzmann constant, Boltzmann equation. Okay, again, but for normalization. So therefore, I can compute from here omega R in terms of entropy of the reservoir, and this is equal to A times the exponential of omega R divided, entropy divided by Kb, and this I have dPs dQs. Now what I need to do is just a Taylor expansion, and then I'm done. And then I will close the lecture, because I have to go today. No, so now let's consider the exponent. So this SR, so this is a function, of course, of ER, of the energy of the reservoir, and this can be written as E total minus ES, where ES is the energy of the system. Now, ES, of course, is much smaller than E total, because the system is much smaller than the total system. And then this can be written as SR of ET. Then I have a minus the derivative of SR with respect to ET, in which case I'm basically assuming that this is a function of if you want, of ET. Sorry, is a function of its argument, of course, and I have to compute this quantity at ES equal to 0 times ES, the Taylor expansion. Okay. Now, ES is much smaller than ET, and is also much smaller than ER. Therefore, when I do the derivative of SR with respect to ET, is also the derivative of SR with respect to ER. And this, by definition of temperature, is 1 divided by kBT. Okay? Where this T is the temperature of the reservoir. So therefore, I'm almost done in the sense that d omega s now is a constant a times, instead of this exponential, now I can write e to SR of et, which is this term here, times e to the minus es divided by kbt. And then I have a dqs, a dqs. Okay? Now, vediamo come l'ho fatto. So basically, this will be now rho, which defines the canonical ensemble. Okay? So you see that this rho, now this time, is a function of ES and can be normalized. So let's do the normalization first. So if I impose, so let me call C equal to A times e to the S of R of t. So this is a constant. And let me impose a normalization condition. Or a probability density. And the normalization, of course, is that 1 must be equal to C exponential of minus ES divided by KBT dPS dQs, from which I get the value of C. Okay, and therefore rho at the end is equal to e to the minus es divided by kbt divided by this integral, which is a normalization integral if you want, which is es kbt dps dqs. Okay? Now, and I will stop in a moment. So what's the difference with respect to the microcanonical ensemble? In the microcanonical ensemble, the probability density is a constant in the phase space, which is a law, then is 0 outside. Whereas in this case, let me omit, now let us remove the subscript S. And let me write rho as a function of E, which is an exponential of minus C divided by kdt divided by this, that will be basically the partition function, but I will write again as e to the minus C kdt dp dq. This function represents the canonical ensemble. And is properly normalized. And you see that this guy here now is a function of the energy. So differently from the case of the microcanonical ensemble, here I have a dependence of rho from the energy, the total energy of the system. Still, since rho is a function of the energy, the Poisson bracket, now don't remember which kind of bracket I use for Poisson. Quale ho usato? Okay. Anyway, let me write it this way. Poisson bracket from rho and forse l'ho indicato in questa parentesi, non me lo ricordo. Now this is equal to 0, and of course E, H, and D are the same for a classical system. The Hamiltonian and the energy are the same quantity for a classical system. For a quantum system, this will be an operator, but also this one will be an operator. And okay, so this Poisson bracket is anyway is equal to 0, and therefore from the Liouville equation, I know that the partial derivative of rho with respect to time is equal to 0. And therefore, indeed, this probability function will describe my thermodynamics of the system S. Okay? So it will allow me to compute the average values of all the quantities I'm interested in, but these average values now are computed, let's say, in the, well, not let's say, but are computed in the canonical ensemble instead of the microcanonical ensemble. And here the difference that I have a weight, which is the usual Boltzmann factor here, that actually will X, when I do the average, it does this job in the sense that, for instance, if I want to compute the average ensemble of the energy, this will be something like the integral of E will be something like that. What is this average energy, ensemble average energy? Is the internal energy. Of thermodynamics. Okay. Now, of course, now this different. So in the microcanonical ensemble, there is no difference between energy and internal energy, but here there is a difference in the sense that the internal energy is a thermodynamical quantity that depends on volume, temperature, number of particles, and so on and so forth. Whereas the energy is the microphysical quantity that depends on the microphysical coordinates, which means the momenta and the position of the particles, at least in this case, or it can depend on the states of my quantum system. Okay. Now, this average can be computed in a similar way for any kind of observable. So if you have a certain function of P and Q, the average value of O will be the same. That instead of E, I will put O. Ok? Va bene, io direi di fermarci qua, perché c'è una chiamata dopo. So maybe just okay. I will again comment, of course, on this. But now we have seen many times, of course, this exponential, this Boltzmann factor, right? But here, what is important to stress is that E is not the energy of a single particle or the energy of a single state available for a particle. Okay, it is the energy of the total system. So that's why here, in principle, one has to include not only the kinetic energy of the particles, if you want, but also the interaction terms among the particles or possible potentials associated with external fields. Okay? Va bene, riprendiamo giovedì. Allora, poi vi faccio sapere se cominciamo alle 8:30 oppure alle 9, a seconda se mi possono aprire l'aula. Va bene?
Va bene, grazie.
Va bene, grazie.
Arrivederci. Ciao.
Arrivederci.
Ciao.
Arrivederci.
Ciao.